Hello, everyone. An interesting question was asked in the last discussion session on what is the significance of passband of a filter. Let us try to understand it through an example. So, I'm looking at application of filters. One of the major, most useful applications of filters is denoising. Denoising, as the name suggests, means removal of noise from a signal or suppression of noise in a given signal. So consider a practical scenario where you have a voice signal. Let me call it x of t. So this is somebody's voice. Now, if we try to find what frequencies are present in this signal, we could use a tool called Fourier Transform. You will learn how to find Fourier transform of a signal when you study signals and systems in the next semester. Okay, so for now, it should suffice to know that Fourier transform helps us find what frequencies are present in the signal and by how much amount. And understand that when we say frequency, I mean sinusoids, pure sinusoids. Basic idea behind Fourier analysis, and this is an incredibly useful tool that says any signal can be represented as an infinite summation of sinusoids, rather, an infinite weighted summation of sinusoids. Okay, so again, the details you'll study in the next semester when you study signals and systems. But for now, let's understand that Fourier transform helps us find the frequency content of a given signal. If this was a voice signal, that means Fourier transform will give us a particular frequency is present in how much amount. So let me just call it capital XF, okay, where F is in, say, kilohertz. Just for an example, you could have written this as X of omega also. Means the same thing, but omega is in radians per second and F is omega by 2 pi. So the unit of F is hertz. Okay, so it means the same thing, just writing this in terms of F. If this is a voice signal, the Fourier spectrum would more or less look something like this. The majority of power of a voice signal is concentrated below 4 kilohertz. Because the typical bandwidth of a voice signal of human voice is about 3 to 4 kilohertz. So majority of the power of a voice signal will be concentrated below 4 kilohertz. So this is typically how more or less the frequency spectrum of a voice signal will look like. Now another character enters the scene. Say you've got another source of noise. This could be a musical instrument or it could be some high pitched noise in the background, right? So there's some noise. Noise is a random signal and fluctuates very, very rapidly. Let me call this NT. This is noise. And noise signal, because it's usually fluctuating rapidly, it is a high frequency signal. That means if we try to find the frequency content of such a noise signal, it would have more values for high frequencies, right? And let me assume, just for the sake of this example, that this noise has maximum power in the range of, say, 8 to 10 kilohertz. That means its Fourier spectrum looks something like this. 8 to 10 kilohertz. Okay, let me call it N of F. When these two signals come together, the resultant signal is a noisy signal. That means this is the signal that we originally wanted to transmit, but now the only signal that we have let me call it XNT, noisy version of X, and that looks something like this. It has kind of the envelope of the original signal, but this noise is added. That means like this. Noise has been added to the original signal. Because Fourier transform is a linear transform, the Fourier spectrum of summation of two signals is equal to the summation of their individual spectrums. So if we try to find frequency content of this noisy signal, it can simply be expressed as a summation of these two spectrums, of their individual spectrums. So it would look something like this. Let me call it X and F. So frequency content of the noisy signal. Where are we going with this? Our objective is to find a circuit that will remove the effect of this noise. That means in terms of frequency, we need to get rid of this part of the spectrum. So what are we going to use? We can use a filter that allows all these frequencies to pass and does not allow this range of frequencies to pass, or attenuates this range of frequency. Right? So we could use, in this particular case, we could use a low pass filter, or we could use a band stop filter or band reject filter that has a stop band in this range. That means if I have a filter, let me call it H of F. Okay, again, instead of omega, I'm writing it as F in hertz. If H of F looks something like this, this could solve a problem. How? Suppose I feed this noisy signal into a system. So I'm feeding this noisy signal into a system whose frequency response is, say, H of F. This results in a signal called XRT, like recovered version of X. I'm calling it XRT. We could call it XFT, filtered version of X. So another property of frequency analysis is that, so if everything is in terms of frequencies, that means the frequency spectrum of the input signal is known, the frequency response of the system is known, then the output frequency response, that means the frequency spectrum of the output signal, can be written as simply the product of the system with the frequency spectrum of the input. Okay, and again, this is a property of Fourier transform. Details you'll study later, but if I try to reconstruct the original signal from its Fourier spectrum, which is called inverse Fourier transform, we would get XRT back. So this is in time domain and this is in frequency domain. What I'm trying to say is that given a filter, if you know the frequency content of the input signal, the frequency content of the output would simply be a product of the two frequency plots. That means a product of this with this. If this is 8 to 10. How would that look like? If I try to sketch HF and XNF, how would it look like? Let me just superimpose the two. This is how the Fourier spectrum of the noisy signal looked like. And this is how my filter looks like. When I find the product of the two, it would look, because say, this is 1. So this range of frequencies get multiplied with a factor almost equal to 1. And this range of frequencies gets multiplied with a very low magnitude. The product would look something like this. The spectrum of the recovered signal would look like. The output of this filter would look like. The effect of noise has been suppressed. Now, how were we able to do this? We were able to do this because we specifically chose a filter that had cutoff values or that had a stop band corresponding to the range of frequencies we wanted to reject from our signal. right? We wanted to suppress those range of frequencies. So this is the importance, this is the significance of knowing the passband, knowing the cutoff frequency, because only when we know what is the cutoff frequency would we be able to apply this kind of a filter in any practical application. This particular application requires us to get rid of frequencies from 8 to 10 hertz. That is why we chose a band reject filter that had a stop band between 8 to 10 kilohertz. In this particular case, we could have also used a low pass filter, because anyway the signal does not have any high frequency content, right? So it's already zero. So there's nothing to preserve above 4 kilohertz as such. We could have also used a filter like this, something that preserves everything up to 4 kilohertz and below it suppresses everything. This is also a filter that would have worked in our case, because 4 kilohertz is somewhere around here. So you would not have anything here, you would have just got zero. The signal still would have resembled the original voice signal very, very significantly. Okay, this is an application of filters in denoising and the significance of knowing the pass band, stop band, and cutoff frequency of any given filter. Another thing is that the standard low pass or high pass RC or RLC filters that we've seen, their stop band is very gradual. Okay, we had discussed earlier that ideally we want something like this, right? We do not want above a cutoff frequency, we do not want any frequency to pass above the desirable frequency. But in a standard RC or RLC filter, the stop band or the roll off around the stop band is very gradual. Okay. We can bring this nature closer to the ideal filter by increasing the order of the filter and using active filters, which are made using op-amps. So essentially, increasing the order would make the roll-off a little steeper, even more steep. Okay, as the order, say this is first order, this could be second order, this could be fourth order. So if you want better frequency selectivity, you need a steep roll off after cutoff frequency. And this could be done by using higher order filters, again the details of which you'll study in a later course. So here I've got a demo of the phasor model for an RC filter. This demo is from Wolfram.com, so it's a Wolfram demonstration. It has been contributed by Michael Bronstein. I've put this link in the description as well. So you can always download the CDF player and then download this demo and play it on the CDF player. So this is the response being shown for a typical RC circuit. The value of R is set here as say 10,000. The value of C is 10 nanofarads. So we're going to change the frequency and see how the output looks like. So what you see in black, this is the input waveform, input voltage, sinusoidal. The waveform in red is the output across the resistor. And the waveform in green is the output across the capacitor. Okay, if we are measuring it simultaneously in a series RC circuit. And this is the corresponding phasor representation. So to start with, right now the frequency is very low. Let me reduce the frequency further to say 10 hertz, right? At 10 hertz, if you are taking output across the resistor, you see that there is this flat red line, meaning you don't get any output across the resistor. Right now I'm focusing just on the red line. So if I go on increasing the frequency, so it is 3000 hertz, 5 kilohertz, right? What you notice is that as you go on increasing the frequency, the red curve that is representing the output across the resistor, the phase difference between that and the input goes on decreasing, and the amplitude also becomes more and more same. That means the output is almost same as input, right? If I go on increasing the frequency. If I now make the frequency as say 1 megahertz, right? you notice that the red curve superimposes the input signal. That means the phase difference between input and output, if I was measuring output across the resistor, is zero at high frequency. And the output is a pure replication of the input. That means the signal was passed through this system unattenuated. So what we notice is that at high frequency, signal is allowed to pass. At low frequency, we get a very low output, right? So if we had a series RC circuit and output was being measured across a resistor, this shows that such a circuit would work as a high pass filter. It will allow high frequencies to pass unattenuated, and it will suppress low frequencies. Now if you look at the phasor diagram on the left, again this is what we observe, that the red line is corresponding to the output across the resistor, right? So as we go on increasing at high frequency, you notice that the length of the phasor across resistor is almost same as that of input. If I go on decreasing the frequency, the length of the phasor starts decreasing, eventually becomes very small. If I now make this say 10 hertz, you notice that it becomes, if I zoom it and show you, it becomes almost zero, right? So length of the phasor represents the RMS value of the signal, and on the right hand side you notice that the signal is almost zero. That means at low frequencies you do not get any output across the resistor. Now let us observe the behavior across the capacitor. The output across the capacitor is shown in green here, light green. So if you notice, at low frequencies, the output across the capacitor and the input waveform are nearly coinciding, are nearly superimposed. That means there's hardly any phase difference. The amplitudes are also same. If I reduce the value of frequency to say 10 hertz, we see that they are identical. They are superimposing on top of each other perfectly. As I said, the black line is showing the input signal, right? So on the phasor diagram, this is a zero phase and this is 90 degrees out of phase, right, for capacitor. And so if I increase the frequencies to say 1000 hertz, you notice that the phase difference between the input, that is black arrow, and the green phasor, which is output across capacitor, there's very little phase difference. That is what is shown here in graph. If I go on increasing the frequency, the phase difference between the input and the output across capacitor goes on increasing, shown here. The length of the phasor is also decreasing, as you notice. That means the corresponding amplitude is also decreasing. Go on increasing the frequency, the length of the phasor goes on decreasing, and the phase difference between the two also goes on increasing. We are following the green line right now, right? As we go on increasing the frequency, the output across the capacitor becomes smaller and smaller and smaller. And if I increase this 10 times, you notice that the output across the capacitor is nearly zero. So what we observe here is that while measuring output across the capacitor at low frequencies, the signal is allowed to pass unattenuated, while as we increase the frequency, the signal is severely attenuated. So this kind of a filter, this kind of an RC circuit, when output is being measured across the capacitor, acts as a low pass filter. You're welcome to download this and check out this demo for yourself. Thank you.